Hey guys, welcome to the Raptors, a digital platform of the RAPT Excellent Tutorials. We started a quick revision series targeting board exam, CBSE board exam for chemistry, which is scheduled for February 28, 2026. We already started with physical chemistry, that is solutions, and in that series we will first very quickly go through what we already did last time, and then we'll proceed ahead in this session. So stay tuned guys, let's proceed with this revision. Solutions are made up of salt and solute, and then there are parameters how to find. So here we will dealing with only homogeneous solution and binary solutions. Homogeneous means uniformly distributed solution, and binary is like just two component, a single solute and single solvent. There are parameters to express concentration. We are done with molarity, molality, and mole fraction. So let us quickly see what are those. So molarity is number of moles of solute per liter of solution. So molarity M is given by WB into 1000 by V into MB. Now let us try to find out the uh, what these letters mean. M is molarity, WB is weight of solute in grams. So in solution we generally have a solvent A, which is solvent, and then you have B, which is solute, and when you mix this solvent to solute, this solute to the solvent, you get a solution. This is AB, which is solution. So WB is the weight of the solute in grams. Now V is volume of solution in milliliter. Yeah, and MB is molar mass of solute. Similarly, we have molality, where M is it is defined as mass of solute per kilogram of solvent. That is small m is given to WB into 1000 by WA into MB. So you know small m is molality, WA is weight of solvent in grams. WMB is same and WB is same. Then you have mole fraction. So mole fraction of a component is equal to number of moles of a component divided by total number of moles. So it is expressed by this letter chi. Chi of A will be number of moles of A by total number of moles. So we have binary solution. So chi A into chi A plus Na plus Nb. Suppose if you want to find chi B, so Nb by Na plus Nb. What is Nb? Number of moles of B. So if we add them both, chi A plus chi B is equal to 1. That's what we did last time. Now we also saw solubility. So if you come to solubility, So it expresses the amount of solute dissolved in a solvent. So we can find solubility of different solvent and solute composition, like gas in liquid. We can also find out for liquid in liquid, and then we can find out for gas in gas. Uh, so solid in liquid, and then gas in liquid. Now, when solids are dissolved in liquid, for example, you have common salt dissolved in water. The solid and liquid, how the solubility changes. So solubility increases with temperature. For example, NaCl in water. So solubility, what happens to solubility? It increases with temperature. We all know that if you increase temperature, the solubility of salt, solid in liquid, increases, right? Now pressure. So pressure has very little effect, little or ignorable effect on solubility. Let me divide this portion. Yes. Now we're going to do gas in liquid. For example, CO2 in soft drinks, O2 in water, etc. This is governed by Henry's law. What is Henry law? It says the solubility of a gas in liquid is proportional directly is directly proportional to the it is directly proportional to the mole fraction of the gas above the liquid surface. So partial pressure of a gas is directly proportional to mole fraction of the gas, and then the proportionality constant is Henry's constant. Now if you plot graph for it, it looks like this, very much straight. So this is partial pressure and this is mole fraction. Slope of the graph is the Henry's constant. So kh idhar, kh is Henry's constant and it is given by slope of the graph. See, y equal to mx plus c, so it is a equation of straight line where m slope is given by Henry's constant. Now we go to liquids in liquid. Let us see the effect of pressure and temperature of on solubility of gas in liquid. Effect of pressure increases the solubility. Because if you see, we'll do those portions later. Let me find space for it. So you have liquid and gases surface over the surface of the liquid. Suppose you have smooth frictionless piston, and if you push it, what will happen? The solubility see, there is increase in solubility. So if you press it harder, more and more gases gets dissolved. So solubility increases with pressure. So effect of pressure, it increases the solubility. That is, increase in pressure increases solubility. Now effect of temperature. Now what happens if you increase temperature? These gas molecules will attain some kinetic energy, and if they attain kinetic energy, they will start moving faster, and then they may eventually escape out of the solution. So see, the atmosphere is getting warmed up. So there is global warming. The side effect of one of the side effect of global warming, apart from melting of glaciers, ice caps, and all, that increase in temperature will cause oxygens dissolved in oceans, rivers, and water to escape the water, which will endanger the marine and aquatic life systems. And since food chain and food waves, we are connected to food chain and food wave, so it can ultimately harm us. So that is one of the effect of global warming. So you see, effect of temperature, increase in temperature decreases the solubility of gas in liquid. So we saw its applications of Henry's law. We saw scuba divers. What happens when scuba divers go deep down the ocean, or say river? What happens? The water, so you have two pressures, atmospheric pressure and gauge pressure. So total pressure due to atmosphere as well as the water column over the body causes more and more gases to get dissolved in blood. So nitrogen getting dissolved in blood causes a phenomenon which is known as bends. So what happens? Nitrogen gets, since nitrogen don't gets used in our body, it gets clumped, and then it causes a phenomenon of bend, which the clumped nitrogen gas causes obstruction in signal flow through our body and causes the phenomenon of bend. So, phenomenon of bend. So, to prevent this, oxygen cylinder composition is helium 11.7%. So you have helium 11.7%, nitrogen 56.2%, and oxygen 32.1%. So this example is important. In your board exam, this example can be asked: what is typical composition of oxygen cylinder of a scuba diver? Now the next example, next application is anoxia. What happens on mountains when mountain climbers go on mountains? Pressure is low because there is very little thin layer of air above one's head. So less pressure causes less oxygen or the air getting dissolved in one's blood. So since oxygen supply is low, brain can't function, or like functions with limited capacity. So this causes dizziness and unable to make clear decision. So that phenomenon is known as anoxia. So these are the two examples of Henry's law. So guys, we are done with solubility of solids in liquid, and then gas in liquid. Now we go to liquid in liquid. So I'll extend this. We come to liquid in liquid. For example, milk and water, or milk has got many components. I'm just giving you an example. You can see alcohol in water. Alcohol in water, so it is perfectly homogeneous and binary. Milk has got so many components, so that is not a good example of a binary solution. Okay, remember we have homogeneous binary solutions in syllabus only. So alcohol in water, and this is governed by Raoult's law. So just like in Henry's law, we have the same like relationship. Partial pressure of a volatile like solvent or solute over solution will be directly proportional to its mole fraction. Now here the proportionality constant is different. It is pure vapor pressure. So let us try to understand what is pure vapor pressure. Suppose you have uh, suppose one has just one liquid, just water. Suppose you have water. Now the pressure and the vapor pressure of just water will be pure vapor pressure. It is just P naught of water. Now suppose if you add alcohol, if you add alcohol to it, so this vapor pressure is just is pure vapor pressure of water. If you add something here like alcohol, then then vapor pressure will be not only due to water, but it will also be due to some amount of alcohol. So you see the vapor pressure uh, contribution from water falls. So it depends on the amount of water present in the solution. So this is pure vapor pressure. We could plot a graph for it. Now what will be PB? Similarly, PB will be proportional to mole fraction of B, like the other component, and then Pb will be given by P naught B chi B. Therefore, total pressure P total will be P A, partial pressure of A and partial pressure of B. So we have P naught A chi A plus P naught B chi B. Now, since P naught A chi A, P naught B, since chi A plus chi B is 1, so we can write chi B equal to 1 minus chi A. So it can become P naught B plus solve chi A P naught A minus P naught B. So you see total pressure, total vapor pressure can also be calculated if one of the mole fractions are known, chi A or chi B. So this is usefulness of the Raoult's law. Now if you plot graph for partial pressure, so this is PA or PB, here as well PA or PB, and this is mole fraction. So here you have chi A equal to 0, chi B equal to 1, chi A equal to 1, chi B equal to 0. So the mole fraction at this point, the mole fraction of A is 0, you just have component B, so component, it will be pure pressure of component B, because there is no component A is 0, so you just have pure pressure of B. Now as the mole fraction increases, chi A will increase from 0 to 1 and then chi B will decrease from 1 to 0. So the pressure, partial pressure will keep on falling, and at the same time chi A will increase, so it will go to P naught A. Now this line represents total vapor pressure, so P total is equal to PA plus PV. So this is a Raoult's law graph. The next solubility we can have is of gas in gas. Gas in gas, for example, O2 in N2, just like our atmosphere. So this is governed by Dalton's law. Dalton's law of partial pressure. So what it says? It says that total pressure, partial pressure A is directly proportional to mole fraction of A. Just like Henry's law, Raoult's law, the Dalton's law also says that partial pressure is directly proportional to the mole fraction of the gas. Now, proportionality constant will be removed and then you'll have P total. The constant, the proportionality will remove and you'll have the proportionality constant, and here the constant is P total. So for other component, one can have PB is equal to P total into chi B. So these are the four solubilities which are there in your syllabus. First, solids in liquid, other gas in liquid, which is governed by Henry's law. It has got applications, and then you have Raoult's law, which governs liquid in liquid mostly, and then you have Dalton's law, which is gas in gas. All of them have got the same structure, that is partial pressure is proportional to the mole fraction, but the proportionality constant is different. Now the question that can be asked in a CBSE exam is, what happens if Henry's constant is increased? So you see, question, what happens to the solubility of a gas in liquid if the Henry's constant is increased or decreased? Let us say if it is increased. Now you have partial pressure of A is equal to Henry's constant into mole fraction of A. Now if you see partial pressure is constant, if Henry's constant is increased, its solubility will fall, the mole fraction will fall. So increasing Henry's constant will decrease the solubility. Now we come to ideal and non-ideal solution. One can have ideal solution and then non-ideal. In non-ideal, one can have a solution having positive deviation and here negative deviation. Ideal solution is one in which delta heat of mixing, the enthalpy of mixing is 0 and volume of mixing is also 0. That is, if you are mixing two solutions, there should not be any change in total heat, or volume should be conserved. That is, if you are mixing 10 ml and 10 ml solution, then this like two solvents, like two components, one is of 10 ml, other is also 10 ml. The net solution volume should be 20 ml. It should not increase or decrease. So if it is increasing, it is positive, and decreasing, it is negative deviation. So in non-ideal, the definition is enthalpy of mixing is not equal to 0 and volume of mixing is also not equal to 0. Why there is positive deviation? It is because there is dissociation. Dissociation is in solution. Why there is negative deviation? Because there is association. In the solution. What is dissociation? Suppose you have two molecules two molecules of A2, and then two molecules of B2. When you mix, the B molecule not only breaks its own bond but also breaks A's bond. So you'll have, the solution will have A, B, A, B. So four single molecule, single like four B's and four A's. So to begin with, you had one A2 molecule, two A2 molecule, and two B2 molecule. That is four molecules. Now you have 8 molecules. So this shows positive deviation. And here you'll have association. That means you have A, and you mix it with BB. When they get mixed together, you find AB. So there is association. To begin with, there were 4, and now you have 2. So number of molecules decreases, so it is association. In both the cases, you have non-ideal solution. Now, ideal solution obeys Raoult's law. They don't obey Raoult's law. Both ideal and non-ideal, but they don't obey Raoult's law. The graph for positive deviation looks like this. For negative deviation, the graph looks like this. This is P total. So you see chi A equal to 1, chi B equal to 0 here. Here chi, see, let me show you the graph properly. Here chi A equal to 0, chi B equal to 1. Same here, chi A equal to 1, chi B equal to 0. Here chi A equal to 0, chi B equal to 1. So you see it has got negative division, it has got positive division. Now in this case, examples are extremely important. Examples are asked that which mixture or solution shows positive division and which will show negative division. So we'll do examples now. So example for ideal solution is N-hexane plus N-heptane, and then bromoethane and plus chloroethane. And then benzene and toluene. So these are three examples. Now in positive division, so positive division examples are ethane plus acetone, and you have carbon disulfide plus acetone. Negative division, examples are chloroform plus acetone and phenol and aniline. So these are two examples, guys. So you see in this positive and negative division, mostly the question that are asked is conditions, graph and example. Sometimes reasons are also asked why there is a positive division, because of dissociation and the number of molecules increase because of that, and in non-ideal for negative division there is association. So you see the corresponding examples you have. Important thing which can be asked in your exam is azeotropes. What are azeotropes? Let us find out. These are the binary composition which have same composition in liquid as well as in the vapor phase. Liquid and the vapor phase. And they boil at the same temperature. It is thus difficult to separate them. So what are azeotropes? Binary composition which are same composition in liquid as well as in the vapor phase, like the vapors that are just above the liquid. So they have same composition. Now they boil at the same temperature. The problem is the composition. The composition is such it will boil at the same temperature. So it is very difficult to separate using fractional distillation or distillation method. And yeah. So there are two types of azeotropes. One is minimum boiling, other is maximum boiling. So there is minimum boiling azeotrope and the other is maximum boiling. In minimum boiling, it shows positive deviation from Raoult's law. And its example is 68% nitric acid plus 32% water. So this is maximum minimum boiling. No. In minimum boiling you have, sorry, this is for maximum boiling. In minimum boiling you have 95% ethanol plus 5% water. Similarly, the maximum boiling shows negative deviation from Raoult's law. And it is 68% nitric acid plus 32% water. So in azeotrope, water azeotropes and what are its examples for positive and negative minimum and maximum boiling azeotropes? This question can be asked in your exam. Examples are extremely important apart from the concept. Now the next important topic is colligative property. What are colligative properties? So the properties which depend which depends upon the number of dissolved solute rather than their type or quality. So colligative properties are the properties which depend upon the number of solid particle dissolved in a solvent and not their types. So there are four colligative properties. One is relative lowering of vapor pressure. The second one is elevation in boiling point. Third is depression in freezing point. Fourth is osmotic pressure. Now, you see, suppose you have a solvent. It has got its own vapor pressure, pure vapor pressure. These are vapors. So you call it pure vapor pressure. P dot A. Now, when one mixes or dissolves salt in it, then the solution contains salt dissolved in it. These salt molecules are not only just in the bulk of the solvent, but also on the surface. What happens? The point where salt molecules are present, solvent can't escape from those points. So what happens? The vapor pressure falls. So you see there is a relative fall in vapor pressure. So the first colligative property that we see is relative lowering in vapor pressure. So you see, instead of pure vapor pressure, we see partial vapor pressure, just partial vapor pressure. So what is partial vapor pressure? PA is equal to P naught A chi A as per Raoult's law. What is change in pressure? Change in pressure will be initial pressure minus final pressure. So it will be P naught A minus P naught A chi A. So if P naught A is taken constant, it will be P naught A chi A. What is P1 minus chi B? It is P naught A chi B. Now, relative lowering will be delta P by P naught A will be chi B, and chi B can be NB by Na plus NB. NB is weight of solute by molecular mass of solute divided by weight of solvent by molecular mass of solvent plus weight of solute by molecular mass of solute. Now you see, since solute are generally dissolved in very small amount as compared to solvent, so we can ignore this. So relative lowering in vapor pressure comes out to be WBMA divided by WAMB. So this is approximate calculation. Percentage lowering can be obtained by delta P by P naught A into 100. So it will be WB MA by WAMB into 100. So this is percentage lowering in vapor pressure. So this is the effect of, we see the effect of lowering in vapor pressure due to a mixing of salt. If the salt amount is appreciable, then we can't we can't take this to be 0, then we'll have to take this expression altogether. So we need to be careful when this expression is only valid only when the amount of solute is very small as compared to the solvent. Now we come to elevation in boiling point. So when a liquid boils when atmospheric pressure is equal to vapor pressure. Now you see, because of lowering in vapor pressure, one needs to heat it up, higher to a higher temperature. Then only more and more vapor will come out, and then only it can match atmospheric pressure, and then liquid will boil. Otherwise, it won't boil. So, what is elevation in boiling point? It is given by delta TB is proportional to molality. So, elevation in boiling point will be given KBM. What is Kb? Kb is known as ebullioscopic constant. It is also known as molar elevation constant. How to define ebullioscopic constant? It is the elevation in boiling point for 1 molar solution. That is, for m is equal to 1, one gets delta TB is equal to Kb. Now come to depression in freezing point. So you see, this is also given by delta TF is proportional to molality. Delta TF equal to Kf into m. Kf is known as cryoscopic constant. And it is same for m is equal to, if the solution is 1 molar, delta TF is equal to Kf. So it is defined the same way. It is the depression in freezing point for 1 molar solution. So depression in freezing point for 1 molar solution. Now there is application, when it snows, very harder in like in low temperature region. So salts are sprinkled on road. Why? Because salts, when sprinkled on road, will lower the melting point of the ice. So if the melting point of the ice gets lowered, it won't freeze. The water won't freeze. So after salts are sprinkled, ice on the road melts, and then roads are cleared off. So this is the application of depression and freezing point. Now let us come to the last colligative property, which is osmotic pressure. So osmotic pressure is a phenomenon when fluid flows from higher concentration of solvent to a lower concentration of solvent. A general example will be like soaking raisins in water. What you do, you soak raisins in water, you dip it overnight, and then what you see, the raisins have got swollen up. It is because water molecule will enter this resin, because water is concentration is less inside, water concentration is greater outside, so water will naturally move from higher concentration to the lower concentration, obviously through a membrane which is semi-permeable membrane. So let's see. One has a semi-permeable membrane, semi-permeable membrane. Now, on one side, suppose there are two pistons which are fixed, which are movable, smooth, frictionless. So, one side you have higher concentration of salt and there is lower concentration of salt. You see, fluid concentration on compartment B is higher, solvent concentration is higher here than on A. So, naturally, the fluid will flow from A to B to A. So if fluid is flowing from B to A, there is pressure. This pressure is known as osmotic pressure, and this phenomenon is known as osmosis. So this osmotic pressure, pi is given by CRT, where C is concentration, R is the real gas constant, and T is temperature. You see this formula, pi is pressure, osmotic pressure. If you look carefully, this expression is very familiar expression. It is actually derived from ideal gas equation. So you have ideal gas equation, PV is equal to nRT. You divide V, so see n by V RT, n by V becomes concentration. So this pi is written in different letter. Pi pressure is denoted by pi. So this n by V is concentration. So CRT. So you see, ideal gas equation has been transformed into uh, mm, osmotic pressure expression. Now, the fluid flows because of the osmotic pressure. Now, there is some pressure. Now, if that pressure is applied on this side, the pressure P is applied on the higher concentration side, and like equal to this osmotic pressure or more than this osmotic pressure, then there will be net flow of fluid from low concentration to higher concentration. So when fluid flows from low concentration of solvent to the higher concentration of solvent, when solvent flows from low concentration of solvent to the higher concentration, by application of external pressure through the semi-permeable membrane, this phenomenon is known as reverse osmosis. So this is RO, that is reverse osmosis taking place. So we have RO filters and all, RO UV and all, like we use like water filter. So that those water filters are based on reverse osmosis. What happens? The tap water, which has more solvents which are not useful to us, are the fluid, the water, the pure water is flown from the lower concentration of fluid to the higher concentration through the reverse osmosis. So they are called known as ROs. So this is phenomenon of reverse osmosis and osmosis. The last topic which we have is Van't-Hoff factor. Now we'll do Van't-Hoff factor just after that. The next topic, which is extremely important, is Van't-Hoff factor. So what happens when the solution don't behaves normally, like when there is abnormal behavior? So there are two kinds of abnormal behavior. One is when the solutions gets associated, and in the other case when it gets dissociated. Suppose one has a solute like AlCl3, it will dissociate as Al3 plus 3Cl minus. So to begin with, the solute had just one molecule, and when it gets dissolved, it produces four molecules. Now we know that colligative properties depend upon number of molecules and not their type. So this solution is going to cause different values for colligative properties, not as expected as a single molecule, because it is giving out four molecules. And in other cases, like so this is case of dissociation. In association, you see two molecules of, suppose, acetic acid, they gets associated to form dimer. So it looks like this. So oxygen is negative, hydrogen is positive, there is intermolecular hydrogen bonding. So it stays like dimer. So you know, two molecules, you had two molecules to begin with, and you just have one molecule after you dissolve in a specific solution. So this changes the expected value of values for the colligative property, and these are taken care of by the factor which is known as Van't-Hoff factor. So what is formula for Van't-Hoff factor? It is represented by I, and it says it is normal molar mass divided by abnormal molar mass. It is also equal to observed colligative property divided by calculated colligative property. And it is also equal to total number of molecules of solute after association or dissociation divided by total number of molecules before association or dissociation. So what you see, in this case, the total number of molecules before association is 1, dissociation is 1, and after it is 4. So Van't-Hoff factor in this case will be 4 by 1, which is I. Here, before you had 2, and after association you have 1. So Van't-Hoff factor in this case will be 1 by 2. So how this Van't-Hoff factor will take care of colligative properties? So the colligative properties now, number one, relative lowering in vapor pressure. Delta P by P naught A is equal to I WBMA WAMB. So you see, all the colligative properties will get multiplied by this Van't-Hoff factor, which is I. Now the other one, elevation in boiling point. Delta TB is equal to I KB into M. Third, the depression in freezing point. delta Tf is equal to I Kfm, and the osmotic pressure will be given by pi is equal to ICRT. So the Ventov factor will accordingly modify the colligative properties. So Ventov factor is for solute particles which show abnormal molecular mass. For association will be it will be smaller than 1, and then for dissociation it will be greater than 1. Now Ventov factor is calculated using this formula, and the colligative property accordingly modifies to this. You just have to multiply by I. So that's all we have from solutions chapter.